What if the problem with gravity is not that we are missing a new field, but that we are misunderstanding how gravity responds to structure? Before going further, let me clarify one important point. By information-based, we do not mean a fundamental information field or a new microscopic degree of freedom. We mean an effective gravitational response that depends on the late-time structural organization of matter. In this video, I want to show you something very specific, not a speculation, not a new particle, not a tuned model, but a concrete numerical result. We reconstructed an effective gravitational response directly from data and then checked whether that same response explains multiple independent observables without refitting. Let me explain what that means. Modern cosmology usually explains late-time tensions by introducing new components, dark energy models, modified gravity parameters, or additional fields. In most cases, those models are proposed first and they're fitted to many datasets at the same time. Here we did something different. We fixed the background cosmology to standard ΛCDM. We did not modify the expansion history. We did not use CMB data. We did not introduce lensing modifications. Instead, we asked a much simpler question. What effective gravitational response is required to explain the observed growth of structure at late times? Concretely, we reconstructed the function mu of z. This function represents an effective, scale-independent modification of the gravitational response that affects only the growth of matter perturbations at late times. We did not assume a parametric form. We did not tune a specific model. We reconstructed mu of z directly from growth data, primarily redshift-space distortion measurements, with optional inclusion of weak lensing amplitude information. That is step 1. Step 2 is the crucial test. From the reconstructed mu of z, we predicted another observable, the EG of z statistic. EG of z combines information from galaxy clustering and lensing, and it is often used as a consistency test of gravity. Here is the key point. We did not fit EG of z. We predicted it. We took the reconstructed gravitational response, propagated it forward, and compared the result to independently computed EG of z values from our locked numerical baseline. This is what we call a closure test. Why is this important? Because in physics, a model that truly captures something real should not need to be refitted for every observable. The same underlying response should explain multiple phenomena at once. In short, the same key should open multiple locks. So what did we find? Across a range of reconstruction choices, different redshift binning, different prior strengths, with or without a weak lensing input, the reconstructed MI of z predicts EG of z at the percent level. Typically within about 1 to 3%, this agreement is robust. It does not disappear if weak lensing information is removed. It does not depend sensitively on the reconstruction details. And importantly, the negative sign branch does not close in the same way, revealing a genuine asymmetry rather than a numerical artifact. What we did not need is just as important. We did not modify the background expansion. We did not include CMB information. We did not introduce additional lensing parameters. We did not perform a global multi-parameter fit. This was a reconstruction-first analysis, followed by a forward prediction and closure check. To make this fully transparent, all numerical tests discussed here are documented in a locked technical report. The report includes the reconstruction pipeline, robustness test, and a diagnostic closure score. It is publicly available with a DOI so anyone can inspect the numbers. The link is provided below the video. What does this mean? It does not prove a specific microscopic theory. It does not claim that gravity is made of information. What it shows is something more modest and more solid. That late-time cosmological data are consistent with an effective gravitational response that can be reconstructed directly from observations, and that this response coherently explains multiple independent probes. This shifts the question. Instead of asking what new field should we add, we can ask What response does gravity actually exhibit in the structured universe we observe? Looking ahead, this reconstruction-first approach is particularly well suited for upcoming surveys such as Euclid. Rather than fitting large parameter spaces, we can reconstruct effective responses, test closure across observables, and let the data tell us how gravity behaves at light times. This is not the final answer, but it is a concrete, testable step forward. And the numbers are there for anyone who wants to check.